for 6, and they have ABC, which probably means that one of these things would be worth 2 points. Fine. Oh, let me get my timer going. Here's my timer, my 10-minute timer. Let those little grains of sand count down my stuff to get these 4 points, I hope. Some building materials contain small capsules filled with paraffin wax to improve the insulating properties of the material. Melting and freezing of paraffin inside the capsules in a material helps to regulate temperatures. Paraffin wax melts at 37 degrees Celsius. That's on a hot day, it'll start to melt. While the wax is melting, the net flow of thermal energy from the wax to the surroundings, or from the surroundings to the wax. Wax is melting. Melting is endothermic. You're breaking bonds. You've got your solid block together. The delta H is equal to positive. So we've got our potential energy down here, and the potential energy moves up. So therefore, we're putting energy into the system. So the thermal energy goes into melting. So let's see. Well, wax is melting. It's an endothermic reaction. We've indicated that. Energy goes into melting the wax. We have our enthalpy, my energy. Okay, good. We've justified our answer. We indicated this endothermic. We've answered it goes into the wax. So I've answered the surroundings. So on a hot day, some of that heat melts the wax rather than heating up the house. Good. Calculate the amount of thermal energy that is required to melt 15.2 grams of solid paraffin wax when the temperature of the surroundings is above the melting point. So we've got 15.2 grams of wax. We've got to change that into moles. Multiplied by, oh, that's nice. Well, they didn't give us the formula, so there's no choice. Wax is almost a polymer. 16.26 grams per mole. Let me get my calculator out, and we'll divide 15.2. Let's see, where's my 15.2? 15.2. Here's my 1 scale, 15.2. And when you divide, you put the number we're dividing by 282. There's 2, 5, 6, 7, 8, 282. My answer is going to be about, my guess is in the area of, I only get 2 significant digits out of this, 542. Now, this is going to be less than that. This is going to be times 10 to the negative 2 moles. And then I'm going to take my 5.42 moles and multiply that by, times 10 to the negative 2 times 48.78. So I take that number here and multiply by 48. There's 8.78, so it's close to 9. And that's going to give me, my guess is, here we go, 2 equals 2.6, and I'm guessing that last value, 2.62, and let's see, times, that'll just come out to 262. This would be kilojoules per mole, And so that's our kilojoules of energy that we need for this. Maybe double check this if you like. But 5 times 4 is about 20. It's going to be right. That's the extra point. Now, when wax melts, the density decreases. Provide the particle level explanation of this observation. Well, we've got our wax with intermolecular attractions packed together, a certain volume. When they melt, we've broken those bonds and they're further apart. So, molecules are further apart after melting. We've broken those bonds. So density is equal to grams by volume. Volume increases. And I've done the particle level explanation. Molecules are farther away. Particle level, you talk about molecules. There's, my guess is to give us 2 points here. One for finding the moles, one for doing the kilojoules. And that's it. A, B, C. We've done 6. And look, we got time left over. Holy cow. I could double check my calculation here. Let's see if that did work out. 15.2 divided by 282.62 times 48.78. Make sure I got the numbers. 48.78. All my numbers are there. Hey, yeah, 2.62 kilojoules. And when I first started teaching, this is the only calculators we could use.